Welcome back to The Explainer. Today, we are taking on an absolutely massive, high-stakes topic. We're going to translate the incredibly complex IEC engineering standards, specifically documents like IEC 6079-14, into a logical, totally practical safety framework. We're talking about hazardous area classification and how we keep multi-billion-dollar offshore facilities from literally turning into fireballs. Let's get right into it.
I want you to think about this for a second. An offshore FPSO, a floating production, storage, and offloading vessel, is essentially a giant floating refinery packed with explosive hydrocarbons. You've got heavy machinery, intense electrical currents, and combustible gases everywhere. So what stops a single microscopic spark from destroying the entire platform? The answer isn't luck, and it certainly isn't guesswork. It's precise, provable engineering. Here's our roadmap for today. We'll start with the anatomy of ignition, then map the hazard zones, and look at engineering the equipment shield. After that, we'll cover gas groups and temperatures, certification and compliance, and finally, competency and exam structure.
All right, Section 1, the anatomy of ignition.
Okay, let's dive into the fundamental problem we're actually trying to solve here. It all comes down to the classic fire triangle. To get an explosion, you need three things: flammable gas, oxygen, and a spark or heat source. Now, here's the reality of an offshore platform. You cannot completely eliminate the gas, and you obviously can't eliminate the oxygen. So our entire engineering strategy must focus 100% on controlling that third element, the spark. We do this in 3 steps. We classify the physical space, we engineer specific equipment protection, and we legally verify it all.
Moving on to Section 2, mapping the hazard zones.
Let's map the danger across the facility using international standards. We rely on the rule of 3 for zones, which dictates exactly what kind of equipment is allowed and where. Zone 0 is an area where explosive gas is present continuously. Think deep inside a cargo tank. Zone 1 is where gas is likely to pop up occasionally during normal operations, like in a pump room. And Zone 2 is where gas is pretty unlikely to appear, but if it does, it's only there for a short time, usually around vents or relief valves. To really picture this, notice the stark contrast in these environments. Your Zone 0 red areas are continuous, extreme danger zones. Compare that to the gray areas, the living quarters, or the control room. Those are classified as safe spaces, where standard industrial equipment is perfectly fine to use. Your location on the rig heavily dictates your engineering requirements.
Which brings us to Section 3, engineering the equipment shield.
So, once we know exactly what zone we're in, how do we actually build the equipment to survive there? Well, this perfectly illustrates the 4 primary philosophies engineers use to protect gear in explosive zones. You can contain the explosion, prevent the spark entirely, starve the spark of its energy, or physically separate the gas from the electronics. Let's break down the most common ones. First up is XD, which stands for flame-proof enclosure. Now, the crazy thing about XD is that we actually allow the gas to enter the box and we fully allow the explosion to happen inside it. But the enclosure is built so incredibly strong with highly specific engineered gaps. As the explosion tries to escape through those tiny metal gaps, the metal cools the internal flame down so much that by the time it reaches the outside atmosphere, it just can't ignite the platform. And here is a golden rule for you maintenance crews: absolutely do not paint the flanges. Paint changes the gap width and completely ruins the cooling effect.
Next is XE, which is increased safety. Unlike flame-proof boxes, XE equipment doesn't contain an explosion at all. Instead, its whole philosophy is pure prevention. It's manufactured to such a ridiculously high standard, with premium insulation and super secure connections, that it simply prevents a spark or a hot surface from ever occurring in the first place.
Then we have what I'd call the ultimate protection, intrinsic safety, or XI. Think of this as literally starving the spark. Engineers design the circuitry so that even if there is a short circuit, the electrical and thermal energy is physically too weak to ignite the gas. Because it's so incredibly safe, this is the primary method used in those highly dangerous Zone 0 environments.
Now, what's really interesting here is that protection isn't just a bunch of passive steel boxes. If you look at the offshore rules for active alarms and continuous monitoring, it's pretty intense. For example, if you're using pressurization, XP, to keep gas out of a space, you must have active alarms hooked up directly to the central control room. If the pressure drops, the system trips. Safety is a highly active, ongoing process.
All right, Section 4, gas groups and temperatures.
But wait, we're not done yet. Knowing your zone and your protection type isn't enough. We also have to factor in the specific chemistry of the hazard. You see, Not all gases ignite the same way. The IEC standards divide gases into groups. Group 2A is for gases like propane. Group IC is for highly volatile gases like hydrogen, which require much stricter tolerances. You absolutely have to match your equipment to the specific gas. On top of that, you have temperature classes, which strictly dictate the absolute maximum surface temperature your equipment is ever allowed to reach.
Think about this number, 200 degrees Celsius. In our source documents for the Baobab FPSO project, engineers mandated a minimum T3 temperature class across the board. That guarantees the surface of the equipment will never, ever exceed 200 degrees Celsius, which ensures it stays well below the auto-ignition temperature of the surrounding hydrocarbon gases.
Let's move to Section 5, Certification and Compliance.
So the engineering is done, but how do we legally prove that this equipment is actually safe to install on the rig? We prove it with highly specific certification strings. This is an actual ATEX string from our source documents. To the untrained eye, sure, it looks like a random password, but to an electrical engineer, this string is the ultimate proof of legal and safe compliance.
Let's read this like an engineer and break it down character by character. X means it's certified. EX2G tells us it's for above-ground use, specifically in a Zone 1 gas atmosphere. EXD proves it uses that flame-proof containment method we just talked about. IC means it can handle the most easily ignited gases, and T6 means its surface will never get hotter than a very cool 85 degrees Celsius. Listen, if this nameplate doesn't perfectly match the hazardous area drawing, it cannot be installed, period.
Finally, Section 6, Competency and Exam Structure.
But who actually gets to sign off on all this? Listen, certifying for hazardous areas is not some multiple-choice quiz you can just cram for the night before. Industry standards, like the CompEx scheme, combine rigorous theory with a hands-on practical bench assessment. Because a wrong answer on paper and a wrong terminal wired in the field carry exactly the same catastrophic real-world consequence. Technicians follow specific skill tracks, XO1 and O2 for electrical installation and inspection, XO3 and O4 for instrumentation, or X11 for mechanical engineers handling flame-proof joints. But if you want to move from doing installations to actually doing the engineering we've discussed today, designing the classifications and selecting the gear, you have to pass X14. That is the advanced certification that specifically tests design and specification.
And here is the real kicker. These certificates expire. Think of it exactly like a commercial pilot's license. You don't just pass a written test once and get to fly forever, right? You have to sit for periodic simulator checks because the stakes are incredibly high. ATEX certification works the exact same way. It requires regular renewals and resits of those hands-on bench checks. If an engineer lets their certificate lapse, they completely lose their authorization to sign off on ATEX work until it's renewed. The industry demands provable, ongoing competency.
And that ongoing competency is absolutely crucial, because an offshore platform is a living, breathing machine. Hazard zones are not permanent fixtures. Routine maintenance or opening up a tank can instantly change a perfectly safe gray area into a deadly Zone 0 red area. This is exactly why strict management of change procedures are vital, and why inspectors have to use intrinsically safe tools, like certified ATEX cameras, to do their jobs without accidentally becoming the ignition source themselves.
Which leaves us with one final thought to ponder. We have seen how meticulously we have to map, engineer, and certify every single square inch of an offshore facility. But knowing that a simple maintenance task can shift these invisible boundaries in an instant, well, it forces you to look at your own operations differently. Are your hazardous areas truly static, or are they shifting right now while you aren't looking? Thanks so much for joining me on this deep dive into hazardous area classification. Keep learning, stay safe, and I'll catch you on the next explainer.